yesterday, but I'm going to just in case. So I did not record one of them. So we'll see what happens. All right. What is the minimum degree of the polynomial function whose graph approximates the given graph? What must the leading coefficient have? Okay, I want to do a little bit of an algebra for STEM review. When you were in algebra for STEM, you did graphs and polynomials, and you talked about far left and far right behavior. Okay, so that's what this question is referring to. So I'm going to give you the function f at x equals 2x to the fifth plus 3x minus 1. And we're going to talk about far left, far right behavior. Okay. All right. So I always start with the far right. The leading coefficient will tell you your far right behavior. Now, again, that's assuming that this is in descending order. Okay. So quick question. What is the degree of this polynomial? The largest exponent.
What degree?
What's the no, I'm not asking. Okay. You're giving me the max number of bends, which we'll get to. I want to know what is the degree of this function? 5. It's the largest exponent. Okay. I'm not asking you to do anything with it other than recognize. Okay. All right. So my far right behavior, what am I looking for to determine if my far right is up or down? The sign. Okay. This is a positive 2, so the far right is up. Then the exponent is your far left behavior. Now we're looking at, is it positive or negative? No, sorry. I said that wrong. No, not positive or negative. Even or odd. Okay, it is an odd number. So what does that tell me that it does in relationship to this far right? Is it the same, meaning it's up, or is it the opposite, which means it's down? It's opposite. So this would tell me then, whereas if this was a 4 or a 6, they would both be up. Okay. All right. So there's some kind of graph in between those, but we know the far right is up and the far left is down. Okay. So the other thing that we're going to be looking at is, and this is what you were thinking of, was the maximum number of bends. So now, when I taught algebra for STEM, which it's been quite a while back that I did, and I believe Mrs. O'Neill still does this, but there was kind of an acronym that would help you of all the characteristics of a polynomial that you needed to know. And it was FISM. It was far left and right behavior. Now, all we're going to be looking at is the far left, far right, which we did. I'm going to go through them quickly. We're not going to do all of them for this problem, okay? Far left, far right, initial value, your zeros, max number of bends, multiplicity. Okay, so we're doing far left, far right behavior, which we just did. And the other one we are going to look at is this one, which is our max number of bends. Now, you already told me it was what? 4. How did you get that?
Because there's always subtracted 1.
You subtract 1 from the degree. So in this problem, it would be 5 minus 1, which is 4. So the max number of bends is 4. So that would mean 1 bend, 2 bends, 3 bends, 4 bends. There you go. Okay, so this is what we're going to be applying to these. So what we want to look at is, so here's A. We're not going to find the full function or equation. That's not what we're doing. But we do have a function f at x And we want to determine if the leading coefficient is positive or negative. And we want to determine the exponent. Okay? All right. So to determine if it's positive or negative, that is determined by your far right behavior. So since this far right is going down, is my leading coefficient going to be positive or negative? Negative. So I'll do it in pink since I did that in pink. Okay? All right, and then I'm just going to do X. I mean, it could be 2X, it could be 3. We don't care. All right, we just want to know, is that negative? Okay, and then the other thing that I want to know is what is the degree of my function? So I want to know the exponent. So I need to look at the number of bins and do what?
Add one.
Add one. So I have 1, 2 bins plus 1, so I know that this is cubed. And so we're going to do that same thing. So I go to B, F at X. I'm going to look at the far right behavior. It is up. So I know that the leading coefficient is what? Positive. I'm going to go ahead and put a plus, but of course, you know, when it's positive, we don't typically, but just so you know where it came from in notes. And now I want to know my degree or my exponent. So how many bins do I have? And so we're going to just kind of quickly go through that. I think you got the hang of it. F at X. So this is far right is down. So we know it's negative. I'm going to go ahead and write it in notes just so if somebody needs it in notes, it's there. We have 1 bend, which makes sense because this is a quadratic, which means it makes a what? Yeah, parabola. And this is negative, which is why it goes down. All right, so D. We're back to up on the far right. So we know this is positive. We have 1, 2, 3, 4 bends. So 4 plus 1, x to the 5th.
Let's make sure it goes from far left to far right.
I'm not sure I understand your question.
Like for example, in D. So I know it's positive because it starts on
the far right always tells you positive or negative. That's where I start.
Yes. So far left to far right. It goes.
Well, this is what dictates. So this dictates that this is a positive coefficient. That's where I start. I think it's easiest to do that first. Okay. So I don't determine, we read and write left to right. So if you want to start with far left and then determine far right, you can do that. Okay. But to me, because far right is either up or down, depending on if this is positive or negative, to me, that's the easiest thing to start with first. And then once I know what's going on in the far right, whether this is even or odd, if it's even, they're both up. If it's odd, they're opposite. It's odd, they're opposite. It's even. If this is down, this is down. Does that make sense? Yes. Yeah. I got that C. Yes, I know that one. All right. Anybody else have any questions? All right. So what we're going to look at now is how to find the inverse. Now, you did do this in algebra for STEM, but it's been a while. So I'm going to give you the steps that you're going to follow. So these are the steps that you're going to follow to find the inverse of a function. Step 1, you are going to substitute f at x with y. Okay, so let's look at this first one. All right, so I'm gonna move over a little bit because we're gonna need a little bit more room. So this is just saying in place of f of x, replace it with a y. That's all that first step is saying. All right, step 2, switch the X and Y. So I'm just going to switch them. So now this is going to say X equals the square root of Y plus 1. All right, step 3, solve for Y. All right, so now I have my X that's all by itself. Now I want to solve it for Y. All right, so the first thing that I'm going to do is I'm going to square both sides because that is what gets rid of that radical. So now I have X squared equals Y plus 1. And then I'm going to subtract 1 from both sides. So X squared minus 1 equals Y. So we've technically solved for Y, but I'm going to go ahead and switch those because we're used to seeing the solved variable on the far left. So I'm just going to rewrite that as Y equals X squared minus 1. Now, a lot of students want to stop here. That was the hardest thing in algebra for STEM. They would neglect the 4th step, and that is to replace Y with F negative 1 at X. That's your inverse notation. So F negative 1 at X. So this tells me what the inverse of that function is X squared minus 1. So we have found the inverse. Now, if that's all it asks you to do, then you're done. I am going to remind you how you are to check this. We can always check to make sure we are correct. You don't have to, but you can. Okay, so how we check it is we are going to come up here to the original equation, F at, and we're going to put the inverse in, which is X squared minus 1. So that tells me I'm going to look at the square root of, and in place of that X, I'm going to put X squared minus 1. And then I still have this plus 1. Now, think back in your wheelhouse and see if you can pull it out. Does anybody remember when I simplify this, if I achieve a particular answer, I know my inverse is correct? Does anybody recall what I'm wanting to achieve? It's down there deep. Okay, let's see what happens. What'd you say? No, we don't have to factor. But thank you for, hang on, you'll see it. Okay. Technically, these parentheses are not necessary. And I have minus 1 plus 1, that's 0, it's gone. So I have the square root of X squared, which is what? What times itself is X squared?
1.
No, if I had 1 squared in there, it'd be 1. What times what is X squared? X. If you do this calculation and you get an X, then you know your inverse is correct. Now, it works both ways. Let's say I would have started with the inverse and a function in here. Then what I would do is take this, whoops, and in place of that X, I'm going to put the square root of. So I'm going to do the square root of X plus 1, and that is squared minus 1. And I'm going to simplify. This squared cancels out that radical, so you're left with X plus 1 minus 1, and you're left with X. So you can always check your work. We're not going to on the next one, but I just wanted to remind you of that. All right, so we're going to go through these 4 steps. So I'm going to replace F at X with Y. I'm going to switch my X and my Y. And now we're going to solve for y. So I'm going to subtract 2 from both sides, and I get x minus 2 equals y cubed. Okay, what am I going to do to both sides to get rid of that cubed? Nothing to factor. Let me ask you this. If I had y squared equals x plus 3, and I wanted to solve for y, what would you do to both sides? Take the square root, right? That means there's a 2 there that we don't write. I'll write it there to give you the hint. That cancels that. You're left with y equals the square root of x plus 3. We don't have a square root, we have a cube root. So what do you think we're going to do to both sides? We're going to take the cube root of both sides. Now I do have to write the cube root. So we get the cube root of x minus 2 equals, and what times what times what is y cubed? Y, because this cube root cancels out that 3 and you're left with y. And then of course we replace, and I'm now going to switch this. I'm going to replace that with the inverse. So we have the inverse notation equals the cube root of x minus 2. And I'm not going to check this one, but you could. Okay? All right. All right, so ultimately we're going to sketch a graph down here. Sketch the graph of the function by hand. Now, notice I left some spacing. Whoops, you can't see it. All right, this is the graph for sine of x. This is what it looks like. I specifically left some spacing here because I want to put an A here and a B here. So technically what we have is y equals 1 sine of 1x. You just don't, when you see y equals sine x, you just don't see the ones. Okay, because what I want to talk about, and we need to remind ourselves, is something that you did in trig. Amplitude. Amplitude is how it goes up and down, up and down, up and down. Does anybody remember how to find? Okay, how to give that to, you are correct, it is 1, right? It goes up to 1, down to 1, so you can look at the graph to see it. What is it here?
The period?
Nope, I want to know where the amplitude is found here. Is it the A or the B? It's the A, and it is the absolute value of A. So, of course, in our case, it is the absolute value of 1, which is 1. Now, sometimes this might be positive, sometimes this might be negative. What happens if it's -1? How does your amplitude is still 1? It fluctuates back and forth, but it tells us how it starts. What would it do?
On the opposite side.
Yes, well, this went up to 1. If this was -1, it would have gone down to 1 first. Just a reminder. Okay, now we're going to get to the period. That is 2 pi divided by b. Okay, so in our case, we have a is 1 and we have b is 1. So for this, it is 2 pi over 1, or 2 pi. So that tells me that I have a complete cycle every 2 pi. So then from 2 pi to 4 pi, you would have another complete cycle. That's what that gives us. Okay, in the interval, anybody remember how to find that? It is your period. So that's our 2 pi divided by 4. So and it's always 4. So we would have 2 pi divided by 4. Simplify that, that is pi over 2. Okay, so you'll look right here. This is pi over 2. Here we have pi, which could also be written as 2 pi over 2. So you here's your first interval, second interval. Here's our third interval, 3 pi over 2. And then 4 pi over 2, which is 2 pi. So pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. And of course, these two simplify. Okay, so now remembering that, we're going to look at this and we're going to sketch it. Now, my sketches aren't very good, y'all. I'm just going to give you a fair warning on that, okay? All right, so I want to start with the amplitude. All right, so in this case, what is my A?
3.
Well, that's my amplitude, but what is A? -3. A is actually -3. My amplitude is the square root of A, so it is 3. So we know it's going to fluctuate between 3 and -3, and we already talked about it. That negative means it's going to do what first? Go down. All right. Period. 2 pi over B. Okay, well, what is B in this problem? What number? 2. Here's your A, here's your B. Okay, so we're going to do 2 pi over 2 or just pi. So a complete cycle is going to cycle in between 0 and pi, where up here the complete cycle went from 0 to 2 pi. So it's kind of going to be squished in more. All right, our interval is always your period divided by 4. Always divided by 4. Okay, so if I were to look at that, then here is pi over 4. Here is 2 pi over 4, which is also pi over 2. Here is 3 pi over 4. And then, of course, this line right here is 4 pi over 4, which is pi. All right, so we know it's going to go down to 3 first, and then it's going to hit a pi over 2, and then it's going to come up to 3 here, and then here. So I am not very good at this, but I'm going to try my best. Whoops, I meant to. Yeah, it should go through there. Like I said, I don't do it. I meant to go through there. So yes, it does. I got wobbly there. Okay. All right. So before we start the next problem, let's have a quick. Oh, and I meant to bring it. Did I? Let me see if I have it. Please have it. I think I have the formula sheet I told you we use most often. I meant to make sure that I had it today because I wanted to show you something. You have the one? Okay, thank you. All right, so you did 30, 60, 90 right triangles in trig. Let's say this one is 30 degrees. Okay, all right. Who can tell me the sides?
1,
Okay, where does 1 go?
opposite to the 30.
Opposite to the 30 is 1.
Then square of 3.
Uh-huh.
I mean square root of
Where does it go? Is it the leg
yes.
or the
the
hypotenuse?
leg.
Okay.
It's 2 on the hypotenuse.
Whoops. Yeah, and then this is 2. All right, and then you did 45 by 45. So what is that one?
Right, your hypotenuse is square of 2.
Okay. All right. So evaluate the expression without using a calculator. Hint, make a sketch of a right triangle if need to. Okay, so let's notice it's the cosine of sine inverse of 1/2. So let's review what this represents. So let's look at this right here. That is some degree of an angle. So what this, when you see the inverse, here's what it's saying. It is asking you what degree has a sine of 1/2. Okay, so am I going to be looking at 30, 60, 90 or 45, 45?
30, 60, and 90.
Yeah, hint, your 2 is not a square root, right? So, yeah, okay. All right, so what degree has a sine of 1/2? Okay, so 1/2 we can look at that, well, it depends on what. So we have 1/2, so it is going to be opposite over hypotenuse. What'd you say?
In the quadrant 1.
And it is in quadrant 1, and that's why I have this. I'm going to show you. Which trig has a, or trig function is opposite over hypotenuse?
Sine.
Sine. Now, if you did not remember that, so here was the main formula sheet that I told you to print off. Notice here's your trig functions. So opposite over hypotenuse is sine, okay? All right, so we know that that is, so we're looking for 1/2. It's in the first quadrant, okay? So we are looking for sine. So am I looking at the x coordinate or the y coordinate?
The y.
The y coordinate, here's your y coordinate of 1/2, which is pi over 6 or 30 degrees. So technically then what this is saying is I want to know cosine of 30 degrees, not percent, sorry. Yeah.
We recognize the inverse. For example, the sine is that we're only restricted to sine only, right? Like only.
Are you talking about first quadrant?
When there's an inverse, they have a restriction, right? Like, for example, sine is only like right here. When there's inverse.
I don't think you have to worry. I don't think.
Yeah.
You have to worry about it.
Never mind.
I'm proud of you for knowing that.
Yeah, and I was getting ready to refer to see if you fully knew what she was asking. So, okay, so you can
have the unit circle. Don't worry about it.
Yeah.
Okay, there you go. And then you can clarify her question for me in case I get it in the future. So, okay, so now we're finding the cosine, which is your x coordinate of 30 degrees. So here's 30 degrees, your x coordinate, so it's the square root of 3 over 2. So the final answer that we're looking for is the square root of 3 over 2. Now, I know that in Enid, you had to have all of that memorized, which is great because it's in your wheelhouse of memory. The good news is you get the unit circle for tests. You get this. So there you go. I got a smile. Okay. All right. Now we've answered that question. All right. Now I do want to talk about on, oh, the words left me, but we'll get there. Okay. So we know this is a 45-degree angle, right? So what is the, if I ask you for the sign, that would be 1 over the square root of 2, right? Do not leave it in this form. We do not leave radicals in the denominator. So I just want to do a quick reminder. Of course, you could probably do it in your head, but how we then get that in correct form. So it would be 1 square root 2 or the square root of 2 over 2. That's what I want to see. Okay. All right. Logarithms, properties. It's probably been a while. Don't forget. Like that. Need to be sure and put one in my notes. All right, so we are going to refresh our memory on the properties of logs. We're going to look to expand in this particular problem, okay? All right, so we're given a single log and we want to expand it. So there were some properties that you learned in Algebra for STEM. So in this example, we have a single log we're going to expand. Down here, we have an expanded log that we're going to put into a single log, okay? All right, we have a fifth root. So if I were to use a property, that would be the natural log of 4x squared minus 1 over 4x squared plus 1 to the 1/5. If this was a cube, it would have been 1/3. If it was a square root, it would have been 1/2, and so forth. Okay. All right. And then because both the numerator and denominator are inside the parentheses, then we can write it as the natural log of 4x squared minus 1 to the 1/5 over 4x squared plus 1 to the 1/5. And that's just a log property. Okay. Does anybody recall what the log property is for division? I can separate this numerator and denominator so it's not a fractional anymore. I can separate it as long as I know what that property is. Anybody have? It's an operation. All right. Subtraction. Okay, so that tells me I can rewrite this as the natural log of 4x squared minus 1 to the 1/5 minus the natural log of 4x squared plus 1 to the 1/5. All right, who recalls, if anyone, what we can do with the exponent with a natural log? We can move it. Move it, move it, move it. Can be moved to the front. So now I have 1/5, whoops, the natural log of 4x squared minus 1 minus 1/5, the natural log of 4x squared plus 1. See how we're expanding it? Now, a lot of students are going to stop here because the next one's a little bit more difficult to recognize. Okay, so what I want you to look at is this and tell me if both one of them or neither of them can be rewritten in a different form. Think factoring. I'm asking you to recognize something factoring wise. Yes, we have a difference of 2 squares. This one is not because it's a plus. This one right here is a difference of 2 squares. Okay, so I need a little bit more room. I have 1/5 the natural log. Okay, I can factor this into two binomials. What times itself is 4x squared? 2x times 2x. What times itself is 1? 1 times 1, and a difference of two squares. One of them's always plus and one of them's always minus. Then we still have minus 1/5. This is not a difference of two squares because of the plus, so we leave it alone. There's not anything else I can do to that. Now, the reason we did that is because these two binomials are being multiplied. When we had this division, we could expand it with a minus. Any thoughts on how we can expand this with? It's the opposite of subtraction. Addition! So now this can be expanded. So now we get kind of this long answer. 1/5 the natural log of 2x plus 1. Now I'm going to put plus. Now, this also has the 1/5 natural log. So you still have to put 1/5 natural log of 2x minus 1. And then we have minus 1/5 natural log 4x squared plus 1. So this is in expanded form. So we went from a single log, natural log to an expanded form. And ln, natural log, if it was log, log, same properties apply. All right, so now what we're going to do is we have one that is expanded, and we are going to put it into a single natural log. So ultimately, we just want the natural log, and then we want a single natural log, similar to this. All right, so the first thing that I always do is I'm like, okay, I'm going to take this and move it up here. So if you need to see that, we can do it. All right, I don't want a fractional exponent. How could I rewrite that? Hint, we had it rewritten one way and we changed it to fractional. Now I have fractional. I want to go back to this. So how will I write that as? What's 1/3 mean to do? It'd be cube root, right? Cube root. So I have, whoops, natural log of 3 plus the natural log of cube root of 4 minus x squared minus the natural log of x. All right. Plus means I can do what with these two parts? If we're going to a single log, what will I do with those? That's subtraction. What did I do? I did addition. If I'm going back, what operation is being used? What's a dot mean? Multiplication. So I can rewrite these two and multiply them. So I would have the natural log of 3 times the cube root of 4 minus x squared. And I have minus the natural log of x.
So there's a plus sign.
That's a property. And then what does the minus tell me to do? Andrew, you were saying this. I'm going to divide. So this is my numerator. So here's my natural log. So my numerator is all of this. Division. Why? Because the property tells me that's what minus is. And then my denominator is X. So this is your final answer right here. Okay, I was hopeful to get to this last one, but I did not. Okay, so I am going to assign both review day 1 and review day 2. So what is today, Wednesday? Review day 1 is already set to be due Thursday. I'm going to make review day 2 set to be due Monday because we don't have class on Friday. Okay. So if you want to go ahead and get started on review day 2, by all means do it. We've done most everything. Okay. Okay. So real quick, Zoomers, any question? I'm going to get disconnected. So if you have a question, you may have to message me. Okay. Check my announcements. So, okay. You guys are free to disconnect.